Okay, electron cloud. So it means that the electron always move around the nucleus and it's form atoms. Okay, so the movement of electron around the nucleus. I got a little trouble with Zoom. Just wait me for a second. Do you still hear me?
Yes, we do.
Yes.
Okay.
Yes.
Thank you. So the answer for 26 is D, movement electron around the nucleus. Okay. The next guide. Now you have to take a look on the word isotope. So what is isotope? Isotope is a set of the atom which have the same number of protons but different numbers of neutrons. Okay, so it means that in the isotopes you always have these values. Okay, let's write it here: 8, 16. You always have these values.
Professor, we can't see what you're doing. The screen is frozen for some reason. Like we can see your mouse, but we can't see the next slide.
It's okay, got it. Oh, you look handsome, David. Now you see it? Do you see the movement now?
Yes, we can.
Okay. So as I said, isotopes is the guy who have the same number of protons but different numbers of neutrons. Okay. So the number of protons is shown here. Is the atomic numbers, right? So for all the kind of isotopes, you have the same numbers here and the symbols of the elements. Okay. Different isotopes will show different values here. The mass number. Okay, mass number here is the sum of the number of protons and numbers of neutrons. So when you have a different numbers of neutrons, the mass number will be different. Okay, so from the symbols of isotopes, you will get the information that this one is named oxygens. Firstly, okay, the oxygen will have 8 protons and 8 neutrons. Okay, and the difference between the mass numbers here and the atomic numbers will give you the numbers of neutrons. Okay, so it's also mean oxygens here will have 8 neutrons. Okay, so the answer will be A. 8 electrons, 8 protons, and 8 neutrons. Okay. So okay, identify the correct set of isotopes. As I said to you before, isotope will have the same symbols of elements, firstly. Secondly, they will have the same numbers of protons or the same numbers of atomic numbers. Sorry. And lastly, they have a different numbers of mass. Okay. So in that guide, you will see this one hydrogen, hydrogen, hydrogens, and different numbers of mass 1, 2, 3. So this one will be isotopes. Okay. The second one, carbon, carbon, carbon. What's happened? Okay, thank you. Carbon, 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 and nitrogens. And nitrogens. Okay, so they are different, so they are not isotopes. They are different elements. Okay, The same for the C. And for the case of D, you have a nitrogen, nitrogen, nitrogens, and different numbers of mass numbers. Okay, so A and D will be the right answer. Next one. Oxygen has different isotopes with different concentration. Okay, so calculate the mass of oxygen atom. It means that you have to calculate the average mass of all the isotopes here with that conclusion. Okay, in relation with the concentration of the isotopes. Okay, so we can consider the mass of oxygens in average, right, equal to the mass of the first isotopes, okay, multiplied to the percentage of the concentration of oxygen 1. I will call this one oxygen 1, okay, 2, 3, okay, plus n oxygen 2 multiplied to the concentration of oxygen 2. Okay, and divide to the 100%. Okay, so from that values, you will have a M01, sorry, M oxygen 1 is 16 multiplied to 99.76 plus 17 multiplied to 0.04 and 18 multiplied to 0.2 and over 100. Okay. Okay. So this one is the mass numbers. For more precise, now you have to divide the number of protons, the number of neutrons in the system, and use the AMU here. Okay, the atomic mass unit. Okay, for more precise. You got it?
Yep.
And the last exercise related to the fullerene, carbon 16. Okay, this one is very beautiful. I could say it's a very beautiful molecule and materials on the Earth. And actually, fullerene is not appear by natures. We can synthesize them. And it's not only 60 carbon there. It's not only carbon 60 for fullerenes. It can be many other numbers. Okay, this can be carbon 80, carbon 240, carbon, even with carbon 3,600, something like that. Okay, with very beautiful structures. We call this one is a carbon particle. Okay, another kind of polymorph, like sorry, I get in trouble with my throat. Okay, so the question for this one is the calculate the mass of C60. Okay, now it's very simple. The mass of C60 will equal to the fullerenes, will equal to the mass of carbons, right? Multiplied to 60. Very simple. Okay. The second one, calculate the density. Okay, so density will be calculated by equal to the mass of fullerenes, right? Divide to the volume of fullerene. It's okay. The volume of fullerene here is defined as come from the different distance. It's okay. So what do you think? What should you choose in this case? Okay, so let's imagine in a simple ways. Okay, if you consider fullerene stay alone without any contact with the other, okay, sometimes we can neglect the movement of the pi electrons. Okay, so don't care, you don't have to care about the pi electrons. So you see only the diameters of the fullerene is this one, 0.7 nanometer. Okay. But in the normal case, fullerene is not stay alone. Okay? Fullerene is not stay alone. So we have to consider about the pi electrons around the cloud of pi electron around the fullerenes. Because of this part, we have a contact with the other fullerenes. Okay, so in that case, we consider the reasons of pi electrons will be the diameters of the fullerene. Okay, so from my point of view, we will take the values of 1 nanometer for the diameters of fullerene. It's okay. So from that, you have a diameters here is 1. So this leads you to the radius of the fullerene will be 1/2 nanometer, right? And then volume will be 1/3 multiplied to pi multiplied to r power 3. It's okay. So now you have a mass, you have a volume, and you can calculate the density. Very simple. So, okay. So let's finish of the tutorial number 1, and now we'll move to to the lecture today related to the electronic structures of atoms. Okay. What's happened? Okay, so beautiful slide. Start for all the lectures of fun. So let's remind you a little. As we all clear that the atoms will contain of the nuclear, okay? And then the nuclear is surrounded by the electron moving around the nuclear, okay? So the question is raising, the electron is moving around. This means that they will move with the identical distance to the nuclear or non-identical distance to the nuclear. It's okay? So the stories of the atom will be introduced to you. Start from the last lectures when the Thomson, he found electrons. After that, Rutherford found protons. And then his students, Chadwick, found neutrons. Okay? So I don't know if you know that Thomson is teachers of Rutherford, and Rutherford is teachers of Chadwick. So it's look like a Thomson family in this case, but they contribute a lot into the fight of the findings of atoms. Okay. So the lecture today related to the electronic structures of atoms. And this one will give you some information related to the arrangement of electron in space around the nuclear, okay, and the electron energies. Okay, so you will see that not all the electron in around the nuclear of one atom have the same energies. They have a different energies, and different energy there will let that electron can move in different areas around the nuclear. Okay, so we will try to make clear about that. in these lectures. Okay. So the given fact or the observation come from the electronic structures of atom here is the emission spectrums of atoms. I will explain it after. And then periodic chemical properties of elements too. Okay, as you see that the metal will have a different numbers of electrons compared to the non-metals, sodium and chloride, for example. Okay, one guy stay on the left side of the periodic tables, the other stay on the right side of the periodic tables. Okay, because of they have a different arrangement of electrons in space around the nucleus, and also the electron energy. Sorry. Sorry. So in this case, sodium and chloride show totally different properties. Like sodium prefer to donate electron out, chloride prefer to gain electron in. Okay, and show the different charge on the ions. Okay, in another case, we will take a look, or you will see that potassium stay at the same column with sodium, but lower in row. Okay, they have a quite similar arrangement of electron in space. Okay, so the only difference between potassium and sodium electron is the electron energy. So they led you to a very similar property between sodium and potassium. They are very, very active. The metal, sodium, potassium, quite soft. Okay, something like that. This is we call the periodic chemical properties of elements. Okay, so you will see it more clear in terms of the periodic tables. Okay, in part of the periodic tables. So the light spectrum, what is this? The light spectrum of the elements, what is this? As you know that the continuous spectrums, okay, unlike the white light you see, or the sunlight you see, okay, normally we call this one is continuous spectrums. Okay, so this one will contain of different colors from purple to red, like this. Okay, and normally they have the color of rainbow. Okay. So this one is actually is only the light in the visible range. Okay, longer than visible range, you have IR or infrared. Okay, when you feel something hot, it's come from infrared. Okay, and shorter than visible range, you will have a UV ray. Okay, the trouble with your skin when you expose to the sunlight with long time. Okay, so it's UV light, visible light, and IR light. And of course, we can continue to some other kind of the radiation. Okay, so in the case of visible range, we call continuous spectrum. It means that the light contains all the wavelengths. Okay, contain all the wavelengths. So it can be around 400. Okay, around 400 nanometer of wavelength in this part, and around 750 nanometer of wavelength in this part. Okay, so continuous wavelengths, continuous spectrums, but the light spectrum is a little bit different. Okay, the light spectrum is the contain only one radiation. Okay, it means that the light spectrum will contain only specific wavelength or identical wavelengths. Okay, for example, the case of sodiums. If you excited the sodium by energy from outside, like you heat it up, okay, or you burn it, you will see the color of the flame come from the sodium burning is yellow. Okay, it's similar to this one. In the light spectrum, when you excite the sodium, the only one wavelength will be two wavelength here will be recorded, and it's yellow. Okay, if you you can do an experiment at home. You can take the common sound. Good voice. It should not be here. Okay, so you can try an experiment at home. Let's take your common sound and use a lighter, okay, a gas lighter, and burn it, and you will see the color of the flame becomes yellow. Okay, and another side, hydrogens is a little bit different. Sodium will have more numbers of electrons than hydrogens, but hydrogen show 4 wavelengths. Okay, it's a little bit different, and we can explain it after. Okay, so you know another application of the light spectrum here is the firework. Okay, so you see a lot of color come from the firework in Tet holidays, for example. When we burning firework on the sky, they come from different metals like sodium, like magnesiums, okay, like aluminiums and potassium. Okay, there are some of the metals there. When you burn it, they will make some color, the beautiful colors of the firework. Okay, so this one is the experiments. Why we from that we can define the light spectrums of elements, and we also call this one is the atom emission spectroscopy. Okay, sorry, atomic emission spectroscopy. Okay, so this one is you burn. Actually, it's not really burn in this case. Okay, this one is the hydrogen gas inside the containers here, and you excite it. And in this case, normally we excited by the very high potential, different potential between this one and this one, 2 electrodes. Okay, and when you excited the hydrogen like that, the hydrogens will generate some of wavelength or some photon go out. It's okay, and after that, after it's moved through a prisms here. Okay, on the screen, a photographic plate, you will see some different light, some different line. Okay, and it shows the different wavelength can be emitted. Okay, of different light can be emitted by hydrogens. Okay, in the excited state. So we will see what's happened in this case in several next part. Okay, the other properties or element properties, the periodic properties of the elements, as I said to you before. Okay, some of the metal is very soft, very active. Okay, like lithium, sodium, potassium, and you see the trouble of lithium batteries. Even if you are using it with your phone, with your laptop, lithium batteries. Okay, the lithium is too active, and it's the reason why sometimes you will see the batteries can be explode. Okay, some accidents happen by the lithium battery of the laptop or phone explode. So it's the trouble of lithium. It's too active for the normal state. Okay. In another side, that you have some elements like helium, neons, or argons. It's inert gases. They are inert gases. This means that they cannot react with anything. Okay. So the similar properties of some elements based on the similar arrangement of electrons around the nucleus. Okay, we call it the periodic properties of the elements. Okay. So you see the helium balance somewhere. This one can be a toy for children. Okay, and in laboratories normally we will use some kind of argons bubbles, argon balloon like this. Okay, to maintain the inert azimuth fields inside the experiments. If you have time, let's go to 707 or 705. You will see our experiments using the balloon like that. Okay, but actually, because of the argon gas is quite expensive, so we use the nitrogen for this case, mostly. Okay, so this is some of the introduction about the emission spectrums of atoms and periodic chemical properties of elements. Okay, so now let's go to the deeper thing. Okay, how to explain the kind of facts. So firstly, let's make familiar with the spherical coordinate. Okay, this one is not chemistry. I could say like that. This one is not chemistry. This one is math. Okay, so spherical coordinated. This one is a kind of system to help you define some of the position on space. Okay, so any coordinated will contain origin, okay, and 3 axes, x, y, z. Okay, stay parallel together and give you 3D dimension of anything. Okay, in another side, for the spherical coordinate, actually we are considering the spherical outside. Okay, with the origin stay in the centers of the sphere. Okay, and one position on the sphere like this will be explained or will be represented or exhibited by by 3 vectors. Okay, we call this one is radius. Firstly, this is the distance between this point and the origin. Okay, the second one, this one is the theta angles. Okay, sometimes it's called azimuthal angles. Okay, and this one is explained to you the angles between, okay, the x-axis and the projection of that point to the x0 y plane. Okay, in another thing, you will have a phi angles, or sometimes we call zenith angles. Okay, so this one explains to you a similar things when you have the angles between that point and the projection to the z between the the OG axis and the radius vector. It's okay. So by 3 values of the radius, okay, azimuthal angles, okay, and this one is namely zenith angles. Okay, you can define the position. Actually, it's not really position. A point, okay, on the sphere around the origin. Okay, so let's take a look on that and help me to remember. So to propose or to represent for a position on space, you can use the normal coordinated with origin and 3 axes, x, y, z, or you can use the spherical coordinated with the radius, azimuthal angles, or zenith angles. Okay, there's 3 of them. And let's help me to remember this one. Electron is dimensionless particles. This means that they have no dimension. Okay, you cannot see the diameter of electron. You cannot see the electron have the width is that, the height is that, so it's not up here. Okay, electron is a point and they have no dimension. Okay. So let's take a look back. Let's remember again about the spectral line of hydrogen before. Okay, hydrogen show 4 lines. Okay, in the emission spectrum. Do you remember that? Okay, and from the wavelengths of the emission line, Okay, Professor Rydberg, very long time ago. Okay, he found an empirical equation. So empirical equation, what is this? Empirical equation is the sum of the equation or sum of conclusion from experiments. Okay, so they don't have any of the theory behind. They come from experiments. Okay, it looks like your experience to do something. So Rydberg is give you the experience of himself. Okay, when he calculate the wavelength of the spectral line of hydrogens. Okay, so in this one, you will have a lambda as the wavelength of the spectral line. Okay, in math, RH here we call a Rydberg constant with the values like that. Okay, and n1, n2 are positive integer. Okay, it can be 1, 2, 3, 4, 5, 6, 7, something like that. Okay, so from that one, he can find he can find the relation between the wavelength of spectral line with the integer values n1, n2. Okay. So this one is in terms of the histories after the find of Rydberg. Okay, in around 1900 or 1900, there are a lot of the new discoveries appear. Okay, for example, the work of Planck and Einstein. Okay, Planck explained about the black bodies phenomenon. What is this? Let's imagine in the case you hit iron rod into the very high temperatures. This one become red, right? And then if you continue to increase the temperatures, the iron rod may become yellow, may become orange, and then yellow, something like that. Okay, and after that, when the temperature cool down, so the colors from the hot steel rod, for example, will move back from yellow to orange to red and then become black. Okay, so in the case of Planck, he concludes that actually he gives the information that an atoms, okay, can accept, gain or release amount of energy, okay, a numbers amount of energy, and the smallest amount in that case is named quantum. Okay, it's named the quantum energy, and the atom can only accept or release 1 quantum, 2 quantum, 3 quantum, 4 quantum, something like that. Okay, so in the case of Einstein, he gives the explanation for the photoelectric properties. What is this? This look like the case you see the metals. Okay? You look at the metals. So you see the metal is quite shiny, right? With a beautiful color, shiny. And then this one comes from the photoelectric properties. When you have a light attack to a materials, okay, some electron can go out from the metal, from the materials, or some other photon can go out from the materials. Okay, we call this one is the photoelectric properties of the materials. Okay, so this one, the work of Planck and Einstein to explain the black body phenomenon and photoelectric phenomena is also help you to explain or to understand more about the electron, how electron arrange in atom too. Okay, but for the last phenomena, the spectral line of the hydrogens, okay, or the electron or the atomic emission spectrum. Okay, so there are still a little bit confused between the quantum theories, start with Planck and Einstein, and Bohr, okay, and Bohr models of the atoms. Okay, Bohr assumed the prevailing laws of physics are inadequate to describe all the aspects of atoms, of course. Okay, so like the law of Newton, it's not very clear for the case of atoms. Okay, so in the case of the light spectrum of hydrogens, Bohr will apply or relies on several assumptions like this. Okay, the first one, he considered that the electrons move around the proton with circular orbit. What does this mean? This one is mean that the electron will move in a sphere around the nucleus. Okay, or actually in this one, he's still in the very first state. He considered the orbit here is a plane. Okay, and electron move around in the circles. But after that, he say the electron is moved around the nucleus as the sphere with the identical distance. Okay, or the orbit will have a certain radius. Okay, so electrons move around the nucleus in the sphere, and that sphere will have a radius. Okay, and when the electron only move around the nucleus with certain distance like that, it means that that electron will have a certain definite energy. Okay, so you can imagine that last one, or the first electrons, you have a nucleus here. The first electron is moving around like this. Okay, the second electron is moving around like this. So the second one is moving at the distance to the nucleus higher than the first one. So it means that the energy to keep the electrons moving in the higher distance compared to the nucleus is higher. Okay, because of electron move, nucleus try to hold the electron back. Okay, stay there. So in the case of equilibrium, or in the case of a balance like that, the energy of the electron on higher or farther orbit should be bigger than the energy at the closer orbit. And even in the case you have another electron on the same orbit, it means that the electron will have the same energy. It's okay. Okay, so it's what I said. The electron there will have a specific energy, and we call this one it's an allowed energy state. Okay, and lastly, the electrons, the electrons stay in orbit in this case, will not radiate energy. Okay, so this means that the electron in this case in the orbit will not donate energy to the others. Okay, they keep the energy in the constants. Okay, so by that way, because of the classical physics say to you that the conservation of energy, right? Energy will not change. They just move from the other to another thing. Okay, from the first one to the second one. And the trouble is the electron here is only move. They are not contact with the other. So it's the reason why the Bohr say that the electron here will not radiate energy. This one will not donate donate energy out. Okay. So in this case, energy will be emitted or absorbed by the electron only as the electron change from one to another state. So it looks like the process of the first orbit, the second orbit. Okay, when electron moving inside the orbit, okay, in the orbit, energy will not change. Energy only changes when you have an electron from the first orbit move to the second orbit, or in the reverse way. The second orbit move back into the first orbit. Okay, so in that process, when electron move from this one to this one, normally energy increase. So you need to give energy to the system, and then electron will gain energy, right? So this process here normally is absorbed. energy. And this process here is namely emit or emission of the energy. Okay. So come from that. Bohr can recalculate the Rydberg equation. Okay, recalculate the Rydberg equation, and he consider the energies of the orbit. Okay, energy of the different energy state, allowed state, or different orbit in the atoms here can be calculated by this one. When you have a h is the Planck constant, okay, c is the speed of light, rh here is the Rydberg constant, okay, and 1 over n square, n here will be the numbers of the allowed state. Okay, so you have several allowed state, n number 1 allowed state, the second allowed state, n equal to 2, the next one 3, 4, something like that. Okay, so energies of each state here will be calculated by this equation, okay, or this equation. Okay, the thing you have to note in this case is this one have a minus, okay, minus sign. The reason is energy of the state. Okay, normally electrons stay on one allowed state will be held by the nuclear. Okay, all the vectors of energy of the electrons now will be point into nuclear. Okay, so if you want to break out that electrons, okay, let's consider there are no point to drive to draw. Okay, so electrons will have the vector of energy point to the nuclear. So if you want the electron move out to some other position, okay, you need the vectors of that electrons move this way. Okay, so in that case you have to pull energy to that electrons to move it out. Okay, so it's the reason it means that you have to put some work into the system. So in that case, in the case you have to put work in the system, normally we consider is a positive energy. Okay, so let's remember the energies of allowed state will be minus, okay, or will be negative. So come from that, the Bohr models will say to you about the emit and absorb energy. Okay, emit or absorb energy. As you see, because of energy, or the electron only can move from the different allowed state together. Okay, it means that they can move from the allowed state number 1 to allowed state number 2, or from the number 1 to number 3. It cannot move from number 1 to something like a number 2.5 because of you don't have the allowed state of 2.5. Okay, so in the case here, it means that the energy of atom in the absorption process or emission process will be the different values of energy between states. Okay. Okay, so from the Bohr model we can calculate the different energy between the state will be the same expression with the Rydberg equation. Okay, and in that case from Bohr models we can demonstrate the Rydberg equation. Okay. So actually, from Bohr models here, Bohr model is not wrong, but it's only a part to explain the quantum models, the modern chemistry models we are using in this moment. Okay. In the very first state, in the very first time when Bohr explained about his models, he made a lot of confuse for the quantum mechanics and quantum physics. Okay, but actually, just because of Bohr model is the starting point to explain about the quantum models, he is not reached to the quantum models. Okay, just only a very first part of the quantum models. After that, when Planck, Einstein, and some other guys like Schrodinger's, Dirac, they developed the quantum models of the atoms. Okay, quantum model is also cover Bohr model. Okay, so it's look like that the movement or absorption of energy and emission of energy actually is the process of increasing energy or decreasing energy. Okay, so let's help me to remember. Electron can change from allowed state to another one. If you have a non-allowed state, and normally we don't have non-allowed state, okay, this means the electron can move only from n equal to 1, n equal to 2. Okay, you will never see some electrons jump from this position to this position. Okay, you don't have that allowed state. So in the case of increasing energy, this means that the electrons will absorb energy from photons. Okay, this means you shine a line to the atoms, and then the line will be a photons with wavelength, right? They will donate energy to the electrons, and then the electron will jump to another allowed state. Okay, in another side, if the electron is staying in the higher state, and that state they don't like, the electron doesn't like this state because of the excited state, for example, as when you drink too much of alcohol, you feel excited, but it's quite a bad feeling, right? And with time, you will go back to the normal state. Okay, after you move out all the alcohol out of the body of your body, you will move back to the normal state, right? So drinking alcohol is look like photon donate energy to you to jump to the excited state. Okay, and the process of moving in the reverse way from the excited state to the normal state here, okay, is contain the process of moving out all the alcohol from the body. Okay, so it's look like this case, electrons will go out, will go down from the higher state to the lower state, and at the same time the energy will be released out as the photons. Okay, so you see the process explained to you also the photoelectric process. Okay, photoelectric is you shine a line to the atoms. The atom will give you some different colors. Okay, or sometimes they can generate an electric. Okay, so it's because of the electrons gain energy from the light, and then they move out from the original state to another state. Okay, for metal, for semiconductor, for example, semiconductor have a two band. We call this one a conduction band. Okay, and this band is insulator band. Okay, so when you have a UV light shine here, the electron in this one will move from the insulator to the conduction band. So it means that in the normal state, without light, conductor cannot conduct electrons or cannot be an electric conductor. Okay, but when you shine a light to the semiconductors, electron jump from the insulator to the conductor band. This means that now they become the guy can transport the electric, transfer the electric. Okay, something like that. Okay, so from the moving, absorb energy and release energy in the emission and absorption like that, we will have the conservation of energy in this case. Photon energy is the different energy between two states. Okay, so E1 minus E2 will be the energy of the photon absorbed or emit. Okay, it depends on the direction of the moving of electrons. Move up, you see absorb electron, absorb energy. Move down, you see the emit energy. Okay. So let's help me to answer it. If a compound X absorbs the photon lambda 1, okay, so the process of E1, E2, E1, okay, so they are jumping from lower to higher. They need a lambda 1. It's okay. So when the emit of lambda 2, when it's emit lambda 2, okay, so you see the lambda 2 is different with the lambda 1, right? So the highest amount of the highest energy of lambda 2 is the process of the moving from the allowed state E2 to the allowed state E1, or in the emission process there, E2 equal to E1. Okay. So in the case, you have another allowed state. Let's call here E3. So maybe you will have the movement of the electrons from the E2 to E3. Okay, and this one can be lambda 2. Okay, or E2. Okay, so you see the electron gain only energy from E1 to E2. It means that the energy from E2 cannot move to the farther state, like than E1, E0, for example. It's okay. So it means lambda 2, okay, lambda 2 should contain the energy equal or lower the energy state, a different energy state between E2 and E1. Okay, so you know delta E equal to 8C over lambda. Okay, so you will have a delta E of the process 1 absorbed, okay, should be bigger or equal delta E of the process of the emission process E2. Okay, so now you will have a lambda 1 will be smaller or equal lambda 2. It's okay, you get it? Delta E1 bigger than delta E2, so lambda 1 should be smaller than lambda 2. Okay, so we will have this guy or sometimes this guy. If we consider E2 cannot be the same with E1, as lambda 2 cannot be the same with lambda 1, so you will have a lambda 1 must be smaller than lambda 2. Do you get that? Okay, So this one we have to explain about the line spectrum. Okay, about the line spectrum. The line spectrum, as we said that actually electrons can jump, only can jump from the allowed state. Okay, this means that they only can jump from the first state to the second state. They cannot stay somewhere here. Okay, so you will have a sum of the movements. Electron from the original state or the first state here can jump to the number 2, number 3, number 4, 5, 6, something like that. Okay, and after that, the electrons from the higher state, like number 2, can go back to the number 1. Okay, number 3, number 4, number 5 can go back to number 1, or sometimes they can go back to the just lower state, like from the number 4, they can move to the number 2. Okay, number 4 can move to the number 3. Okay, and each of moving after excited, or each of the process of emit light after excited like that will give you a line on the atomic emission spectrum. Okay, or spectrum line, or light spectrum, sorry. Okay, so the values of 1, 2, 3, 4 here at the time of Bohr models is not named quantum numbers, but at this moment is, as I said to you, Bohr model is only a part of quantum model. Okay, so at this moment this guy will be named n, and it's called quantum number. Okay, so with the Bohr model, the very good thing is the Bohr can explain the line spectrum. But the trouble is the other molecule or the other atoms show much more complicated light spectra compared to hydrogen. As you see, hydrogen have only one hydrogen. We have a structure like that with only 1 electrons. So the movement of electron of hydrogen is the most simple compared to the other. Okay, the other contain at least 2 electrons like helium, or more complicated like sodium, potassium. Okay, with several numbers of electrons. So the Bohr model cannot explain the other, just only explain the hydrogens. Okay, so but as I said, Bohr model is only a part of quantum model. So we are using 2 useful ideas from the Bohr model. Firstly, electron in atom have only certain discrete energy levels, as shown by the n quantum number. Okay, and the second one, energy exchange in moving an electron from one level to another one. This means that the electron, when they move from the first level to second level, they will be absorb energy or emit energy. Okay, or the energy only change in this case. So there are 2 important ideas from Bohr models. Okay, the other idea, like electron is moving in the identical distance to the nucleus, okay, it's wrong. Okay, and after that, the development of quantum physics is up here. So it's very long. Okay, for the quantum physics, they start with the actually it's not start with the Berkeley, but they start with Planck and Einstein from the very first of the 1900s. Okay, Einstein says that the atom have a properties. The light have a property of particles as the photons. in case of the photoelectric phenomena. And then in the reverse way, Louis Broglie say to you that if light have a behavior as the particles, photon, this one is come from Einstein. So the particle should exhibit the wave characteristic. Okay, so the wave show a property of particles. Then the particle should show a property of wave. Okay, and from that, the Broglie equation appear when you have the wavelengths associate with the particles. Okay, so as the atom, as the electron, as the nuclear. Okay, so they have a wavelength too, be equal to the Planck constant over mass of the particles and the velocity in mass per second. Okay, so do you see that? You see that with this one, if you have a quite high mass, okay, a particle with high mass, the lambda will be very small. So this is the reason why when you see a big particles like a cup, like your phone, you will not see the wave characteristic of these things. Okay, because of the mass is too big, right? But for the case of some very small particle like nuclear, okay, you can calculate lambda or calculate the wavelength of that particles to show the wave characteristic of the particles. Okay, so there are some of the applications. This moments tunnel diode, for example, when you see the electron can jump, goes through a quantum realm we call the tunnel phenomenon. Okay, and by that the electron can transfer the information very fast in case of your mobile phone. Okay, by properties we call, or by phenomena we call the tunnel phenomena. Okay, so let's do it at home. Okay, you can calculate the wavelength associated with your weight. Okay, so after Broglie, the other scientists like Heisenberg or Schrödinger and some other Dirac, for example, okay, developed the quantum mechanics, okay, or the physics of matter waves. And by that, in terms of quantum chemistry, one of the most important explanation about the structures of atoms is come from this guy, Schrödinger equation. Okay, so Schrödinger equation will give you the information about the wave properties, okay, or wave function of the system, or very small system like atom or sometimes molecules. Okay, firstly, for quantum mechanics, the main feature will include that a wave cannot precisely localize. What does this mean? What does this mean? A wave cannot be precisely localized because of the particles here still have a mass. Okay, so it means that at the same time you cannot precise. You cannot take the you cannot find at the same time the positions and the phase of the movements of wave. Okay, or is it similar to the uncertainty principles? You cannot define at the same time the wave and the position and the velocity of particles. Okay, and then when the electron behave like a wave, okay, it means that they will not be precisely localized, okay, like a wave. And then uncertainty principles appear. You cannot define the same time speed and the position of the particles, okay, of the particle with wave characteristic like electrons, okay. And lastly, the wave function. The wave function, it shows you the probability of the presence, okay, of the electron in some portion of space, okay, and also give you with the information about the energy of that electrons. Okay, so solving the Schrodinger equation, very complicated like that. And I will not move in this one because it's very complicated, even for the chemists like us this moment. Okay, to solving this Schrodinger equation, they will give you the wave function. Okay, we call this one wave function of C. So the C here will describe the electron in an atom. So it means that the electron now will move around the nucleus in a space, and in that space, or in that area in space, sorry, that area will be described by wave function, including the shape, the size, the direction or orientation of that areas in terms of the spherical coordinated or normal coordinated system. Okay, so by that way, the wave function will give you the probability the electron will stay in that area with the with the sign, the shape, and the orientation. So it's look like this one. A wave function is the probability density of the electrons or the electron density, okay, in a regions around the nucleus. This one is nuclear, stay in the origin of the coordinated system, and the electron is moving around. Of course, they moving with not identical distance to the nucleus. Okay, so wave function only gives you the information about the probability you can find that electron in one position or in one area around the nucleus. Okay, so you see some part, the density of the dot, a blue dot here, is higher than the other. Okay, so it means that the electron will be concentrated in these areas more than this area. Just it. This is the information from the wave function. Okay. So, as I said to you, the areas in that you can find an electron with the highest probability. Okay. Okay. This is defined by the wave function. Okay, or in another way, wave function is a kind of the stationary wave around the nucleus, and it gives you the information about the areas in which you can find the electron. Okay, so that areas can be described by the word orbitals. Okay, and normally in scientific words we can say that the wave function are called orbitals. Okay, but in the imagination you can think the orbital explain to you about the area in which you can find electrons, the electron around the nucleus with highest probability. Okay, so the wave function, of course, is they come from the solution of the Schrodinger equation. Okay, so actually Schrodinger equation for the complicated atoms, the atom with more than one electrons. Okay, normally we give you the set of the wave function, not only one wave function, a set of wave function. It depends on the numbers of electrons. Okay, and also the corresponding energy of that wave function. Okay. So let's imagine we have an orbital now. Orbital come from the wave function and describe about the area in which you find an electron. Okay. So now let's take a look on this. Each orbital, as I said to you, each orbital describe a distribution of electron density in space. Okay. Firstly, this come from the wave function. Explain about the probability to find an electrons or the electron density in space. The second thing, let's have me to remember, orbital has characteristic energy and shape. Okay, so it's not like the electron move. It means that electron actually they cannot move anywhere they want in around the nucleus. Okay, they only move in a space, and that space, move in an area in space, and that area is characterized with the energy. Okay, with the characteristic energy and shape. Some of the orbital we have the shape of sphere. Some of orbital we have the shape of dumbbell, or some other have a complicated shape. Okay, but they have a shape. Okay, identical shape. So normally orbitals in atom we characterize by a set of 3 quantum numbers. Okay, let's have me to remember 3 quantum numbers. Because of actually in high school, with some of you will study that the quantum numbers will have 4 values. Okay, so you will have 4 quantum numbers, but the last quantum numbers is a little bit different, and it did not come from it's not really come from the Schrodinger equation. Okay, Schrodinger equation will give you the 3 first quantum numbers. The spin quantum number will be given into the set of the quantum number here to complete it. Okay, and the reason I will say after. But in the case of solving Schrodinger wave equation, you will have 3 quantum numbers, N, L, and ML. Okay. So let's take a look on each of them. Okay. The first one, N, is namely principal quantum numbers. Okay. This one is the very first quantum numbers, of course. And the values of quantum numbers here is 1, 2, 3. So do you see it familiar?
Yep.
Yeah, thank you. So come from the light spectrum, right? Come from the Bohr model, right? So principal quantum number N here, okay, explain to you about the allowed state, allowed energy state of the electrons around the nucleus, like the Bohr model explained to you. Okay, or we can say the principal quantum number is the meaning is come from Bohr model. Okay, so when you move from 1 to 3, 3 to 1 to 2, 2 to 3, okay, so it means that if you increase the number of N or increase the principal quantum numbers, okay, as we see, you have N equal to 1 is lowest position, and then is N equal to 2, right? 3, 4, something like that. So when you move from the N, the lower values of N to the higher values of N, you will have the higher energy state, right? And I said to you before, higher energy state, it means that the electron can move around the nucleus with the longer distance to the nucleus. Okay, so normally the conclusion is if you have a quantum number increase, it means that the orbital become larger. or we can say that the electron can stay farther from the nucleus. Okay, of course, from the lower state to the higher state, they will contain higher energy. Okay, and when they contain higher energy, actually now because of stay farther compared to, even they have the higher energy, but they stay farther to the nucleus. Okay, so normally that electron is less tightly bound to the nucleus. Okay, or if you can consider the reaction happen or any process happen to the electron of the atoms, normally they will happen with the electron stay farther than the guys stay closer to the nucleus. Okay. Okay, the second one is L, the angular momentum quantum numbers. Okay, or sometimes we call this one as the azimuthal quantum numbers. Okay, so this guy will have the interval values from 0 to n-1. So it means that if you have the values of n equal to 3, for example, okay, n equal to 3, for example, you will have the value of L will be 0, 1, 2. Okay, or it means that from the principal quantum number of 3, the energy state of the level 3, you will have now at least 3 orbitals with L or angular momentum quantum numbers of 0, 1, and 2. Okay, so this means that from the first energy levels n equal to 1, you have only one L. This means that you have only one set of the orbitals. Okay, if you have n equal to 3, now L can be 0, 1, 2, or you have 3 values. This means that you have now at least 3 set of orbitals. Okay, the information from L is the shape of the orbitals. Okay, L will give you the shape of the orbitals. So as you see, now the shape of orbital will be defined with the name, we call this one a subshell. Okay, SPDF. Okay, as this one will be how to say, this will be corresponds with the values of L. If value of L is 0, you will have orbital S, type of orbital or set of orbital S. Okay, if you have L is 1, you will have a set of orbital P. L is 2, you have orbital D, and L is 3, you have orbital F. Okay, and now actually we are stopped at the orbital F. Okay, the guys stay on the in the periodic tables. There are more than 100 elements there, and actually they are stopped at the orbital F. Okay, we still cannot find any new elements in the natures, and also in the laboratories it's quite a hard process to produce new elements. Okay, and normally we are working on the atoms SPDF orbitals, just it. Okay, so this also means that L will have the highest number. Okay, the highest values of L is 3. Let's remember it. The next one, magnetic quantum numbers. Okay, ML, the magnetic quantum numbers. This one will describe the orientation of the orbital in space. Okay, and they have the interval values between -L and L, including 0. Okay, so it means that if you have L equal to 2, you will have the set of ML. will be -2, -1, 0, 1, 2. Okay, or we can imagine that when you have the set of orbital d, right? The set of orbital d. Now you will have a 5 orbital d oriented in space in different orientation. Okay, can you imagine it? Okay, so as you see from the Schrodinger equation, you will have a N, L, and ML. So okay, as I said to you before, this one will give you the information. N will give you the information of size of the orbitals. L gives you information of the shape of the orbitals, and ML gives you the information about the orientation of the orbitals. So, okay. So, from a set of the quantum numbers, now you will have something like that. Okay, with n equal to 1, the very close or the very first energy state from the nuclear, you have only one possibility of L is 0, right? And then L is 0. So it means that ML is 0 too, because of ML just run from -L to L. Okay, so in that case, with n equal to 1, you will have only one orbitals. Okay, and this one is namely 1s. Okay, if you have n equal to 2, now L will be 0 or 1. Okay, in the case of L is 0, again you have ML is 0. Okay, so this one will be named 200 is a set of quantum numbers, and orbital here will be defined as 2s. Okay, but in the case of L equal to 1, now you will have 3 values of ML, -1, 0, or +1. Okay, so in terms of quantum number set, you will have a 3 quantum number set, right? Or 3 orbitals, and they can explain to you about the 3 orbitals 2p. Okay, 3 orbital 2p, and this one can be considered in the case of the space of the coordinated system. Okay, you will have the first orbital stay here, okay, in x axis. The second one can stay here in y axis. Okay, and the third one stay here in z axis. Okay, so we call 3 2p here is 2px, 2py, 2pz. Okay, so it means that in total, with principal quantum number of 2, okay, you will have 4 orbitals, 2s and 3 2p, 1 2s and 3 2p. Okay, if we continue, n equal to 3 is more complicated. Okay, this one gives you the 3s, right? This one will give you 3 orbital of 3p. Okay, 3px, 3py, 3pz. And in the case of L equal to 2, as I said to you before, L equal to 2, this means that you will have 5 values of ML. Okay, so in that case, you will have a 5 orbital of 3d. Okay, L equal to 2, it means that you have a d orbitals. Okay, 3s, 3 orbital 3p, and then you have a 5 orbital 3d. Okay, and continue to n equal to 4. Now you have a 7 orbital of 4f, something like that. Okay. So for the summarize, okay, it's not a lot of information, but because of I said to you all the thing. But let's help me to remember n give you a size, the size of the orbitals. Okay, or another name n can be give you the information of the shell. Okay, of the orbital have a similar energy and similar size. Okay, and second one, L will give you the information about the shape of the orbitals, and normally we call it subshell. Okay, this C can be subshell S, subshell P, subshell D, something like that. Okay, and next one, ML will give you the information of the orientation, okay, in space. Okay, this one is the better way to write down to give you it's not give you actually this is the better way to represent or exhibit the energy levels or orbital energy levels in atoms, not only hydrogen atoms. Okay, so you can see for this one with n equal to 1 you have the lowest energy levels, and in the case of n equal to 1 you have only one orbitals of 1s, right? That's right here with a frame or with a square box. Okay, if you continue to move to n equal to 2, now you will have one orbital 2s and 3 orbital 2p. Okay, with one square box and 3 other square box. N equal to 3, you have a 1 3s, 3 3p, and 5 3d. Okay, something like that. So this one is a better way, easier way to define the structures of atom, structure of the electron around the nucleus of atoms. but the thing is, okay, so sometimes you will see some of the diagram like this. Okay, this diagram explained to you about the probability. This one, probability, the vertical axis is the ability for you or probability to you to find the electron toward the distance. Okay, so for the and here the units of distance is Armstrong. So for 1s normally you can find most of electrons 1s stay around 1 Armstrong from the nucleus. Okay, for 3s, for 2s, sorry, you will have a sum of 2s stay closer to the nucleus than 1s. Okay, and the other part is mostly stay around nucleus with 3 Armstrong in distance. Okay, and let's have me to see if you have a 2s or 3s, you have some position, specific position like this. Okay, and we call this one is the node. Okay, node is a position or a sphere or a plane or anywhere or anything. Okay, but at this position you cannot find electron. Okay, or probability to find electron at the node is 0. Okay, so even you have a electron 2s, you still find some node or 1 node. Okay, for 3s you have a 2 node. Okay, you see a sphere from 3s, but at this position you cannot find the electrons. Okay, the representation in the orbital, as I said, orbital is the area in space that you can find an electron with the highest probabilities. Okay, but actually that areas with the volumes of is only around 90% chance to find the electrons. Okay, you still have a 10% electron will stay somewhere, not inside that area. Okay. It can be some other values, but okay, it's not 100%. You cannot be sure that the electrons stay around the nucleus, okay, in that areas with 100%. This will never happen. Okay, and normally with s orbitals, you will have the shape of the sphericals. Of course, let's imagine the nucleus stay in the centers. Okay. The second one, p orbitals. Normally you have a dumbbell. Okay, so if you go to take some gym training, okay, you will use the dumbbells a lot, right? So by that, you will see, as we explained before, p orbitals or L equal to 1. Okay, you will have 3 orbitals of p. 3 orbitals p. Okay, so 3 orbitals p here will be arranged in a space as the coordinated system. Okay, so one will go along PZ, okay, the z axis, the other go along x axis, and the other go along y axis. Okay, so you have a PZ, PX, and PY. It's okay. So this depends on the values of ML. Next guy is the d orbitals. D orbital is a little bit more complicated. Actually, it's much more complicated. And for the elements with the last electron stay on d orbitals, like transition metals, the property is much more complicated. I could say like that. Okay. So you may see maybe in the next lectures how d elements become very complicated. Maybe it's given to you by phone. So, okay, so let me take a look. Okay, I think I will stop here because of the next part we related to the many electrons, and this will not be complicated after several minutes. So I will stop here, and we still have several minutes for some question if you have.
Professor, I have a question.
Yes.
I think a few slides before you were talking about the subshells, and there was an example where there was a negative number for a subshell. It was
okay. I will go back slow.
Long.
Please point to me. Okay. This one is subshell, right?
Yep.
Is this one?
No, before the slide. Where is
Can you
it?
point out?
I don't remember what slide it was, but no, go back again. You can move forward for it. I think you went back too much.
SPDF?
No, it's not. It's the one after that. I think you can go back. I think it was this one when ML equals -1.
Okay.
Can you re-explain what does that mean if it's -1?
Okay. Actually, let's imagine like this. ML. Okay, I will go back to the state of ML. Okay, found is not right, very clear about that in this one. But ML have a name of magnetic quantum numbers. Okay, so this guy is mean that the ML will relate it to the magnetic properties of the orbitals. Okay, so let's imagine. Now the subshell will related to the SPDF. I will explain after. Okay, and SPDF here with the values of minus. Okay, you need me to explain about the values minus here, right?
Yep.
Okay, so let's take a look. So ML actually, his name is magnetic, okay, quantum numbers. Okay, so it means that actually the orbitals here have the magnetic itself or intrinsic magnetic properties of itself. Okay, so it gives you the case if we consider the magnetic from outside. If you have a magnetic from outside, magnetic field from outside, okay, and affect to the atoms. Okay, so now you have some orbitals like PZ will not be affected by magnetic outside. Okay, but if the orbitals stay in another orientation, they will be affected by the magnetic outside. Okay, some of the orbital will go paramagnetic. All the intrinsic magnetic of the orbital will be the same direction with the magnetic outside. Okay, but some other will have we call diamagnetic. Okay, in that the intrinsic magnetic of that orbital will be in the reverse direction or opposite direction with the magnetic field outside. Okay, so it's the reason why ML can have a values of minus, of negative, to show the opposite direction of intrinsic magnetic of that orbital compared to the magnetic field outside. Is okay?
Yes, thank you for the explanation. I understand now. Thank you.
Okay. Any other question, guys? No? So let's remember again, actually this chapter, the very important part related to the set of quantum numbers. Okay, and I don't have a time to say about the last quantum number of spin. Okay, but let's help me to remember the very first one is the n principal quantum number. We say for the energy of the orbitals, and of course energy of the orbitals will be the discrete energy like a Bohr model. Okay, and this one will be designed for the size of the orbitals. Okay, L is the azimuthal quantum numbers or angular momentum quantum numbers. This one is the shape of the orbitals. If you have a shape of S, this means L equal to 0, and you have a S subshell with the shape of sphere. Okay, if you have L equal to 1, you will have P subshell, and this one have the shape of dumbbell like this. Okay, and in the case of D subshell, L equal to 2, and the shape of orbital is like, let's call it a kind of flower like this. Okay, and in the case of F orbitals, actually it's not stay, the orbital of F is not stay on the plane like this anymore. Okay, the F orbital stay as in space with let's imagine you have a bunch of the balloon. Okay, and it's much more complicated. And the information of ML is what I said to you as explained to David. Is the orientation of the is magnetic orientation, or the orientation of the orbitals is designed by the magnetic of itself. Okay, So I hope you understand about that. And do you have any question? No more questions?
No more questions.
It's okay, it's look good. And we finish on time. Thank you very much. And I hope next week Phong will be continue and give you much more information compared to me. I think so. Okay, thank you very much for coming.
Bye, Professor. Goodbye.
Thank you, Professor.
Bye, teacher.
Thank you, Professor.
You're welcome.
Goodbye, teacher.